Let's just review where we've been now. We've started with the equation of a plane. We found a point on the plane and another point on the plane. Incidentally, we didn't indicate that point on the notes, but that's this point. We sketched 3 lines that lie in the plane to give some indication of about where the plane is. And we've chosen a point 1, 4, -1 that's not on the plane. And what we're trying to do is determine how far this point is from the plane. In order to determine that, we've constructed a vector from this point to a selected point on the plane, and we could have used either of the other points. We could use, in fact, any point on the plane. This works no matter what the point is. Of course, if we choose a different point on the plane up here, then this vector is going to be different. But for this selected point, 0, 0, 12/5, we determined that the vector from 1, 4, -1 to that point is -I minus 4j plus 12/5 k. We also know that the normal vector to the plane, a normal vector to the plane, is 4i plus 6j minus 5k. So that all we have to do to determine the distance from this point to the plane, moving at a perpendicular to the plane, is project this vector onto the normal vector, and the vector perpendicular to the plane, and we'll have the distance. And all we need here is a scalar projection. So let's see how that works. So what we have to do, as soon as we get our focus back, let's see, here we go, is project the vector -I minus 4j plus, let's be sure we got it right, plus 17/5 k onto the normal vector, which is 4i, you can read it off from right here, plus 6j minus 5k. Now remember to project a vector onto another, and we can see this by looking back here. The magnitude of the projection is just going to be the magnitude of this vector times the cosine of the angle theta between the two vectors. If we let this be theta, we can see that this vector here runs along the adjacent side, the side of a triangle that's adjacent to theta, and actually it's adjacent to 90 degrees minus theta, but the cosine is the same for both, so that this is going to equal the length of this vector times the cosine of this vector, and that's going to be the distance of the point to the plane. Of course, we can always review projections to be sure of that. Now, what's the projection? The projection onto n of the vector minus I minus 4j plus 17/5 k is equal to the dot product, -I minus 4j plus 17/5 k, dotted with our normal vector, 4i plus 6j minus 5k, divided by the magnitude of the vector 4i plus 6j minus 5k. Now you should recall from our development of the projection that this is the magnitude of this vector, so when we divide this vector by its magnitude, we're essentially getting a unit vector, which we then multiply by this vector times the cosine of theta. And what we end up with is now just straightforward calculation. We end up with -4 minus 24, and 17/5 times -5 is minus 17, over the square root of 4 squared plus 6 squared minus plus 5 squared. Now that turns out to be -28, -45 if I'm doing my arithmetic correctly. and that's 16 and 6 is 52, so that's 77. So this would be negative 45 over the square root of 77. Now that's not actually a distance, that's negative, and as we see from the picture here, this vector is at an angle greater than 90 degrees with respect to the normal, so the projection actually goes in the direction opposite that of the normal vector, and that's why we have a negative here. If we want to make this into a distance, we just go ahead and put absolute value signs around it. Put absolute value signs around this, absolute value signs around this, and absolute value signs around this, and we find that the distance is 45 over the square root of 77. Square root of 77 is between 8 and 9, a little bit bigger to 9, a little bit closer to 9, say about 8.7, so this is going to be a little more than 5, so I'm going to say that's about maybe 5.2, and no great confidence in that. You can check that out with your calculator. Okay, so we've used this picture, simplified it down to the dot product of two vector, well, the projection of one vector onto another, done that calculation, and we've obtained a number that should be equal to the distance between this point and this plane. Now, had we based this on another point of the plane, moving from 1, 4, negative 1 to, let's say, 0, negative 2, 0, we would have obtained the same distance. Would have made no difference. The projection of this vector onto the normal vector would be identical to the projection of this vector onto the normal vector, or had we used this point or any other point of the plane, we would have obtained exactly the same result, negative 45 over the, or well, 45 over the square root of 77, when we take the magnitude of the projection.